Welcome. Today we'll be talking about a thermodynamic analysis of a ramjet engine, presented by Andrew Morgan and Dan Ritchie. First, a little background on ram engines. Ramjet engines can be traced back to about 1657 when the first example was introduced in a satirical novel by Cyrano de Bergerac, a French writer who, upon his death, some old novels from him were presented and published, and he was accredited for the first idea of a rocket-powered engine. Moving forward to 1913, a French inventor by the name of René Lorin first conceived a patent device resembling a ramjet, which highly resembles those in use today as well. Now we're moving forward to 1933 into more modern age. The first jet-powered projectiles were used in artillery cannons and are supposedly the first projectiles that broke the speed of sound. Going forward to the war days in 1947, where the infamous Chuck Yeager broke the sound barrier. And moving slightly after him was the Gorgon 4 air-to-air missiles developed by Glenn Martin, which utilized a ramjet engine created by none other than the University of Southern California.
So we established a thermodynamic model which we could use at various altitudes. So we decided to do simplified stages of the ramjet. Here at number 1 we have the inlet, and then number 2 is right before compression, and then stage 3 is right after compression. T is the throat of the converging diverging nozzle, and then 4 is the outlet. So we're going to be analyzing these in kind of the 3 phases. So 1 to 2 is the compression cycle, 2 to 3 is combustion, and 3 to 4 is the converging diverging nozzle, where the air really gains speed.
Some assumptions were made on this cycle in the ramjet, they being where the steady state, steady flow condition. So we're saying that the same volume of intake air and exit exhaust will be present throughout the system. We also assume that it was an isotropic ramjet, so losses in the diffuser nozzle structures will be neglected to simplify calculations, where it would be recommended that a real exit temperature would definitely be higher. Thirdly, we did say that we are utilizing ideal gas law, which would be comprised of 78% nitrogen and about 21% oxygen. This is just another easy way to make calculations a little more easy, as nitrogen behaves as an ideal gas among all of the other gas species. We also assume that the exit pressure will be equal to the inlet pressure. So what this will do is just make our conditions a little more reasonable when comparing data for our test series and making sure that we are within reason on that. Normally a ramjet would experience a higher exit pressure than the ambient pressure found in the atmosphere. Next, we did say that we were going to test at level flight and constant velocity, trying to take into consideration acceleration and higher load factors would make this math very complicated. And just to keep a consistent density and composition at a particular altitude will make calculating our variables a lot more easily obtained. Next, we did say it was instantaneous fuel injection. Trying to model kind of a mass flow rate of fuel combusting in an engine can be very tedious, and a high degree of optimization would be required. So we are assuming instantaneous combustion. And lastly, we refer to standard atmospheric tables. What this will do is just give us good ambient temperature and pressure at various altitudes, which will ensure a baseline which we will establish our conditions off of.
So some calculations were performed in 5,000 meter increments for the thrust generated, thermodynamic efficiency, and then TSFC, which is the thrust specific fuel consumption, which is an efficiency factor commonly used for comparing thrust to the amount of fuel used. It can be shown that as the ramjet operates at higher altitudes, the thrust force generated drops dramatically. This also decreases the efficiency of the engine, and this is mainly due to the decreasing density of the air that is utilized within the system. So the air is there's less air being taken in because there's less air there. The efficiencies in thrust-specific fuel consumption level off quickly, but the thrust force does drop in magnitude about 50% every 5,000 meters. This shows that there's an absolute operating ceiling for the ramjet, And this is definitely the case with the SR-71 Blackbird, which has a ceiling at about 25 kilometers, which is about where you'd start losing all thrust, and then you wouldn't be able to accelerate any longer or maintain altitude. This system design could be modified to have different parameters, such as a more optimized area relationship throughout the ramjet. The analysis performed was based off set Mach numbers, and then the exit was Mach 3, and research geometry to ensure valid results. The system also employed an ideal case analysis with minimal to no heat loss during the operation. It had constant fuel delivery and constant specific heat. Further optimization could be performed on the throat and nozzle exit of the ramjet that would facilitate better results on the output system.
So looking forward to what the future holds for ramjets. Obviously, there have been already some natural progressions in the creation of a scramjet, which utilizes supersonic speeds from the inlet conditions to the outlet conditions. And Lockheed Martin has proposed a hypothetical SR-72, which will be the next edition of the 71, which is capable of hypersonic speeds, which is essentially Mach 6 and above. And as you can see, when you're going 4,500 miles per hour, which is about 1.3 miles per second, you can imagine that that speed and temperature will cause that friction to come so hot that it will melt conventional metallic airframes. So reconsiderations on the composite structures and high temperature materials is really a big development that needs to move forward in order for this dream to become a reality. So thank you for watching, and as you know, the engine may go, but the Decepticon will never die.